name's Sydney.
And I'm Katie.
And this is our Chapter 13 Physics Project.
The best physics project
We're
ever!
making history.
Oh snap. Spring force! Amplitude is the maximum distance traveled by an object away from its equilibrium position. T, the period, the time it takes for an object to execute a complete cycle of motion. F, the frequency, the number of cycles or vibrations per unit of time.
What is simple harmonic motion, you ask? It occurs when the net force along the direction of motion is a Hooke's law type of force. That is, when the net force is proportional to the displacement in the opposite direction.
In this problem, we are measuring the spring constant. We are given m, the mass, and we are given d, the distance. What we have to do is we use the formula that Hooke's law gives us, which is F equals kd equals mg, which also converts to k equals mg over d. We use that formula and plug in our numbers, which you see here. These numbers are converted. This is gravity, and this is our meters, converted to meters, because we started with centimeters. Well, you guys get it. So after you plug all those numbers in, you get your answer of 2.7 times 10 to the second newtons per meter.
Elastic potential energy.
Energy stored in a stretched or compressed spring or other elastic material is called elastic potential energy. Energy is stored in a spring only when it is either stretched or compressed. Furthermore, the elastic potential energy is a maximum when a spring has reached its maximum compression or extension.
The potential energy in a spring is always positive! Which leads us to the work energy theorem, which consists of work equals Ke plus Pe plus Pes. Final minus Ke plus Pe plus Pes initial. Get it right there, you know what I'm saying?
A 13,000 Newton car starts at rest and rolls down a hill from a height of 10 meters. It then moves across the level surface and collides with a light spring-loaded guardrail. Neglecting any losses due to friction, find the maximum distance the spring is compressed. Assume a spring constant of 1 times 10 to the 6th. So what we do, since we're converting potential energy and we have potential energy in the spring at the end of the trip, we have to use this formula right here. To find x, we must change the formula around to be able to convert it to this formula. So these two formulas are the same. This one is just finding x. So then what we do is we plug in our numbers. We plug in the 13,000 newtons we have our 10 meters, we have the 2 that we originally started out with, and this is the number that they also gave us in the problem, which was the spring constant. When you put all those numbers together, your newtons cross out and you are left with meters, and you have 0.5 meters is your answer.
Velocity is a function of position.
This is the formula for the sum of the kinetic and potential energy at the final position when you are finding velocity. The plus and minus stand for if you're moving to the right, you use positive, and if you're moving to the left, it's negative. In this mass spring system problem, we are given a mass of 0.5 kilometers, which is connected to a light spring with a spring constant of 20 newtons per meter, which oscillates on a frictionless horizontal surface. The amplitude starts off with a motion that is at 3 centimeters, and we want to compute the kinetic and potential energies of the system when the displacement is 2 centimeters. All we have to do is use this formula that Sydney showed us earlier, and we plug in the numbers. We are given the constant of 20, the meters of 0.5, and the 3 and 2 are the centimeters given for the displacement. You put that all together, and you solve it to get positive or negative 0.14 meters per second.
Uniform circular motion can be described as the motion of an object in a circle at a constant speed. As an object moves in a circle, it is constantly changing its directions. At all instances, the object is moving tangent to the circle. This example can be shown as in a roller coaster doing a loop-de-loop.
A 13-kilogram car is constructed on a frame supported by 4 springs. Each spring has a spring constant of 20,000 newtons per meter. If 2 people riding in the car have a combined mass of 160 kilograms, find the frequency of vibration of the car when it is driven over a pothole in the road. So we assume that the weight is evenly distributed, and we have 4 springs. The total weight of the car, which is 1,300 kilograms, and of the people, which is 160 kilograms, is 1,460 kilograms. We have 4 springs in the car, so what we have to do is divide that number by 4, getting our number of 365. We use our frequency formula, which is up here, and plug in the numbers that we have. They give us this number, and this is the number that we found, and after you plug that in, you get 1.8 Hz. A simple pendulum is another mechanical system that exhibits periodic motion. It consists of a small bob of mass, M, suspended by a light string of length, L, fixed at its upper end. A pendulum's motion is also a simple harmonic, as we have been learning about. A pendulum depends not on mass, but only on the pendulum's length and on free fall acceleration. And that, my friends, is pendulum. A man needs to know the height of a tower, but darkness obscures the ceiling. He does note, however, that a long pendulum extends from the ceiling almost to the floor, and that its period is 12 seconds. How tall is the tower? Well, if we use our formula, T equals 2 pi and the square root of L divided by G, and we switch it around to find L, we get this formula right here. Then all we have to do is plug in the givens. We have 9.8, which is always gravity. 12 seconds is our time, and then we have the 4 pi squared. When motion is said to be damped, the friction reduces the mechanical energy of the system as time passes. As we see in this example here, we have a simple spring with a weight at the bottom of it. When Sydney releases the motion, we see simple harmonic motion. When we add a force of friction into the matter, aka a vase filled with water, and do the same exact spring motion thing as we did before, we see that the motion is quickly slowed down, unlike before. This is an example of damped motion.
When it comes to longitudinal waves, particles move parallel.
With a radio wave having a wavelength of 3 meters, find the speed of the radio wave. We use this formula, V equals our frequency times our wavelength. They give us the frequency, but since it is in mega, we must convert it. So when we plug our frequency into the formula, we do 100 times 10 to the 6th, which is the conversion to get it to what we need. Our wavelength, which they give us, is 3 meters. According to the formula, we just multiply the numbers together, giving us 3 times 10 to the 8th meters per second. This is a wave broken down. As you can see, the top is the crest, the bottom is the trough. Amplitude is this part right here, or right there, from the line to the top. An entire wavelength would be this, or this, or this. The symbol for a wavelength is this baby right here.
Constructive interference is if two waves having the same frequency and amplitude are in the same phase. Now that's like A and B. The resultant wave, when they combine, is C. It has the same frequency as the individual waves, but twice the amplitude. Destructive interference is when two waves with the same frequency and amplitude are 180 degrees out of phase, like A and B. The result, when they combine, is C. It's complete cancellation!
Let's talk about water waves! Yeah!
A water wave moves from one place to another, but the water's not carried with it. The waves have to have some sort of disturbance, a medium that can be disturbed, and some physical connection or mechanism through which adjacent portions of the medium can influence each other.
The superposition principle! If two or more traveling waves are moving through a medium, the resultant wave is found by adding together the displacement of the individual waves, point by point. The superposition principle is valid only when the individual waves have small amplitudes of the displacement.
The end.
And this motion picture has been brought to you by Charlie Incorporated.
A Cap Production Company.